Just to talk a little bit of the scope of what we're going to go over today, we're going to talk from a sequence writing standpoint, looking at this from the SoundCheck perspective, and we're going to assume you have some basic understanding of how to write a sequence in SoundCheck, how to configure hardware, how to calibrate a device. So we're not going to spend any time going over anything like that. We're going to kind of just jump in with these three topics. We're going to start by discussing subsequences, how to use them, when to use them, and what possible benefits they can bring to sequence writing. Then we'll look at step and sequence configuration, specifically how to take steps, create loops out of them, what putting different settings on different steps will do to a sequence run. And the last subject we have is external control of SoundCheck using TCPIP commands. And with that, let's get started with subsequences. In SoundCheck, we can insert entire sequences into another sequence. For how we name it, just to kind of keep track as we go through this section, the sequence that was inserted is what we call the subsequence. The sequence that contains that inserted subsequence is what we would call the master sequence. A master sequence can contain other sequences, so many subsequences, or it can contain multiple steps as well as subsequences. When you add in a subsequence into a master sequence, it's going to appear as a single step. When you expand that step, it will show you all of the steps that were originally created within the subsequence. When the master sequence runs and it executes the subsequence, it will then run every step that was originally created in the subsequence. All of the data that's output from the subsequence is available in the master sequence's memory list. So if I calculated impedance from my subsequence, I could then take that impedance in my master sequence and run it through different post-processing steps, run it through different analysis steps. All of that data is there and available for me to work with. When the steps of the subsequence are expanded, they're numbered independently of the master sequence. So this is just kind of visually how we represent it in SoundCheck. And the easiest way to kind of understand what I'm referring to is to just look at a picture of it. Here is an example of a master sequence that took the subsequence complete test and added it. To add it, we expand the sequence step template from the template editor. This will show us all the available subsequences that we can grab, and I just dragged complete test and put it into my main sequence. Now when I run this master sequence, it's going to behave the exact same as if I opened up complete test and ran that. And you can see when you look at the numbering what I was talking about before. The complete test sequence is step number 1. That's in the master sequence. I expanded this subsequence by clicking on the plus sign to the left, which is now showing the minus sign. And when I do that, it shows me every step inside the subsequence, which are all numbered independent of the master sequence. So it starts back at 1. As you add in more subsequences or more steps into your master sequence, it will start continuing at 2, not 18. So why would we use subsequences? There's a couple benefits that really shine when you're trying to use a subsequence over some other methods of writing sequences. One really common use case is for quicker sequence writing. If you're always writing sequences and starting off with the same stimulus, acquisition, analysis, display, post-processing step, and you're just recreating that same thing every single time, what you could do instead is create a subsequence that's just kind of the bare bones of what you're trying to do in all of these sequences. Then as you're creating multiple sequences that are based off that, you would just drag in your subsequence and be ready to go. So instead of adding in 5 different steps or 6 different steps or 100 different steps, I just grab my subsequence, drop it in, and I can just push start and go. Another thing that would make subsequences very helpful is if you're doing modular testing of similar products. So when I think of this, it's something like I'm testing 20 headsets. They're all pretty close. They all need kind of the same thing, but maybe I only need impedance with one specific change on half of the devices. And maybe I need a different stimulus range on some of them. And a couple of them have left and right when some of them only have right. So I could create a lot of subsequences that test the same thing. So I'd create a subsequence to test THD with the sweep stimulus for 2 drivers. Then another subsequence that's an RTA with pink noise. Then multiple sequences with estimated resonance, etc. Then as I'm going to put together the sequences for all these specific devices, I could just mix and match the subsequences. So one device, I might want to use A, B, and C. Then another device, I only need to use subsequences A and C. Having a library of not just steps, but sequences can make it very easy to put together similar tests very quickly. One other benefit that ties back into the modular testing is that it's very easy to push changes out to multiple sequences. If you think of a normal step template, once you drag it into SoundCheck and you start using it in your test sequence, it's no longer tied back to that original step template. So if I put it into my sequence, I edit it, make a bunch of changes, then I drag that same template into another sequence, then it's just going to be the original template. Any of those changes I made aren't going to be carried over. This is by design. This is how it's supposed to work. We don't want you to be editing one sequence and changing every sequence that refers to the same step template. But what if you did want to do that? If I had a subsequence and 20 different master sequences were referencing that same subsequence, and I said, okay, well, instead of just looking at THD, I also want to look at THD plus N on all of these sequences. What I could do, instead of opening up 20 different sequences, clicking a checkbox, I could go into a subsequence, place those into my master sequences. Then when I edit my subsequence and I enable that THD plus N checkbox, every master sequence that's referring to that subsequence will get that updated data and is going to use THD plus N. So it's very quick. It's a lot easier than going into all of your discrete sequences and making changes. And it's a good way to make sure what you're changing copies through. If you go through and actually make those changes on a one-by-one basis, the opportunity for human error for something to be different is pretty high. And then Going back and troubleshooting, finding the one that's wrong and one that's right will take a lot more time, whereas if you were using subsequences, you change it in one spot, it gets pushed out everywhere else. When using subsequences, there are some rules and specific things you need to think about, though. The master sequence and the subsequence must be in the same exact folder. If we go back quickly to this picture we saw before, this sequence dropdown, where all of these sequences live, this is just expanding and showing me all the sequences that are in the same folder that I'm in. Wherever I save my sequence, when I expand the sequence step template, it's showing me all of the sequences in that same folder. If I move one of the sequences, it's going to break my subsequence. So you need to make sure that if you're using subsequences, they're all saved in the same directory. You also can't edit any subsequence steps from the master sequence. If I had my complete test dragged in as a subsequence and I wanted to change the analysis from my master sequence, double-clicking on that analysis step isn't actually going to open the editor. I would need to close my master sequence, go into my subsequence, open it up, and make the changes. The subsequences are basically read-only. They're going to execute the steps, but you can't open up and edit them. Again, this is good to make sure that nothing is changed by accident. It's to make sure that when you're inside your master sequence, you're only editing the steps that are specific to that sequence. And if you want to make any changes, you have to go and edit them inside the subsequence. Subsequences also shouldn't contain any groups. You can make them and put them in there, but when you drop them into your master sequence, they'll often break, and it's not going to be what you want it to be. It's going to be single files, not in a group. That's fine to know and to work around. You just need to keep it in mind. If you write a very long subsequence that groups together a bunch of waveforms and runs them through one analysis step, when you drop that subsequence into a master sequence, that analysis step is only going to be pointing to one of the waveforms. So instead of grouping together and passing through one step, you'll just need to create steps for every single piece of data that you're trying to analyze, anything you're trying to post-process. It'll just have to be one-to-one, and if you don't use groups in the subsequence, when you open it up in the master sequence, you'll be fine and ready to run. The overwrite or keep repeated data will apply to the subsequence. This is something we're going to visit in the next section when we talk about step configuration a little bit more in depth. But the important thing to remember is that if I have 5 subsequences that are all pointing to recorded time waveform, and I put those subsequences into a master sequence, whatever the setting is will apply in the master sequence. So if I had keep repeated data on, then instead of just one recorded time waveform, I would have 4 different waveforms with the same exact name. And maybe my subsequences 2, 3, and 4 all end up pointing to my first recorded time waveform. So if you have anything that's going to be using the same name, we'd recommend to either add the input data name, add the signal path name, or just give them completely unique names. Don't reuse any names throughout your subsequences. If you do, make sure you're overwriting the data and not keeping repeated data. But the easiest way to do it is just give very specific names, make sure they're unique, and you won't run into any issues. This is similar to the last point. but all of the display steps also must have different names. Just like if you tried to have recorded time waveform 4 different times, if you tried to have display default 4 different times, when SoundCheck tries to open the displays, it's going to put everything onto the same display. That's not what you want to do. So just give it specific names, either prepend them with a number or give them something in context. These rules are also available laid out in the manual. And I would recommend using the SoundCheck manual. And in the chapter for subsequences, there's an area called rules. It's basically everything we went over here with some examples and just how it behaves when you're inside the subsequence. So if you're starting to write your own subsequences, keep this in mind. You can reference this video, or if you have the manual open, just pop it open, read through these rules again, and make sure that you're following what it says here. Very similar to inserting a full subsequence is inserting steps from other sequence. So when we inserted in subsequences, basically the entire sequence would be read-only, everything would be tied down, we couldn't edit it, but every change we made to that one subsequence would carry out through everything that references it. But steps are different. You insert them just like they're any other step template. And just like any other step template, once they're added to your sequence, they really break any ties they had to the original sequence. If I bring in steps from a sequence and edit them, it's not going to change anything from the original sequence. But the drawback is if I went and wanted to roll out those changes everywhere, I would have to go back and edit them manually. But this is a very quick way just to throw in a bunch of steps in a way that you have configured that you want to. The source and destination sequence have to be in the same folder to initially add the steps, just like in subsequences. But once you add the steps into your sequence, this is no longer required. You could go ahead, move your sequences anywhere you want. The step templates are copied into your new sequence. When the steps are inserted into the destination sequence, they're just given numbers in relation to the other steps of the sequence. If I had steps 1 through 5 and I added in another step, it would be step 6, and that's it. We're also going to be using the sequence group template at the bottom of the sequence editor's template library. But now instead of just dragging in the full sequence, we're going to expand it. In this example, instead of bringing in the full complete test sequence, I just want to bring in the stimulus acquisition and 2 analysis steps. I wrote these the way I wanted to. I just want to drag them in here and quickly get THD, rub, and buzz, and impedance. I can expand sequence, expand complete test, then I shift-click to highlight this first 4 steps in the sequence. Then I just drag them into my sequence. Now when I run my sequence, I'm getting the data that I already configured in my other steps. So we talked about some of the benefits of subsequences before. This way, inserting the steps themselves is what I'd prefer if I'm just trying to quickly get up and running and writing a sequence. But it doesn't have the other benefits. It's not as modular and it won't allow you to push out the changes. But when I'm putting together a sequence for the first time, a lot of times I'll just say, yeah, take these 4, drop them in, start running, start writing my sequence from there. So tools are very similar, very helpful, but just remember the two differences. The subsequences can't be edited and are related, and the step templates, once they're dragged in, can be edited and are no longer tied. In the email we sent out, we should have included some hands-on PDF files. I'm going to go over them now and walk through them myself. I'd recommend following along with them, watching what I do on screen, then maybe going back, trying to recreate this yourself using the instructions that I laid out. If you have any questions, ask us. But it's definitely something that I would recommend trying. It's all of these sequence writing techniques and SoundCheck itself. It's something that takes practice. It's something that the more you understand, then the more you try and do an application, it's going to get easier. So watch me work through it here in SoundCheck on my end. Then take the handouts, try and do it yourself. In this example, I have a line of devices that are all pretty similar, and all of them are going to be tested with the same stimulus and get the same analysis, but the limits we'll need are going to be different. I'm going to take them just on different frequency ranges. What we're going to do is write two subsequences. One's going to analyze the data, and one's going to set the limits. As these get more and more complicated, as your tests become longer and longer, do more in-depth things, the more helpful this will be. These examples are pretty short. They're going to be a handful of steps just so we can kind of work through them quickly. But once we have this in a way that we easily can just drop them in and get writing sequences, it's going to save a lot of time in the future. Okay, so first, this is also assuming that we have our hardware configured already, we have our calibration done. I have in Audio Connect with an amplifier, a speaker under test, then a reference microphone. Those are already set up and configured and ready to run. So the first thing I'm going to do is I'm going to create a new directory, and this is going to hold all of our sequences together. Because I need to put all of the sequences and subsequences in the same folder, I'm just going to start with that. So in SoundCheck 18, in the sequences directory, I'll just go ahead, put in a new folder, and I'll call this subsequences. This doesn't have to be in the sequences folder. It could be on a network drive. It could be anywhere you want. Oh, I already have one. So I'll just say no. So I already made this before, so I'm all set. Now, what I'm going to do in SoundCheck is make some new files. So the first one I'll do, I'll just click on File New, get a new sequence going. Then right away, I'm going to save as and drop it into my subsequences folder. I want to make sure that I'm saving these in the same place. That way, when I start referencing them, they're in the same spot to start with. I'm going to call this one Fundamental. Here we go. I'll quickly put together a test. We're going to go out of my amplifier to the stimulus, record in on my reference microphone, and drop in the THD template. So I save the sequence. If I run it, I'm going to be outputting some different curves here. So I'm getting my fundamental, I'm getting my THD, but I'm not going to worry about displaying them or doing anything else with them in this sequence. So I have a sequence that calculates the pieces of data that I care about. I'll save this one. I'll open up a new sequence to create my second subsequence. This is where I'm going to create some limits. On this device, we'll say I care about the limit at 5 kilohertz. I'll call this 5 kilohertz limit and save it. I'm going to insert in the post-processing step template sensitivity. And now we run into one issue that we have to keep in mind as well. So I created a curve called fundamental in my last subsequence. I want to take that and pass it in here. But when I open up this post-processing step and I try and find fundamental, it's not there. I haven't calculated it in this subsequence. So how do I actually point to it? We're going to talk about this a little bit more in the next section, but we can use a feature in SoundCheck that's called sequence parameters. What this does is just create blank curves, values, or waveforms that we could update either by using subsequences or by using TCPIP to externally set these values. So over here, in overall sequence up at the top, I could double click on this and add a sequence parameter called fundamental. And all this does is creates a blank empty circle fundamental curve. There's no actual data here. If I try and view it, it's completely empty. But what will happen is I'll make a master sequence. I'll put this subsequence after the first one that we just created, where the curve was named fundamental. And as the sequence runs, it's going to fill in that fundamental data curve. Here, I can now point to my fundamental. Now I'm just going to change this to actually take the sensitivity at 5K. I'm going to enable the search range, right-click in here, and add a single point. The single point is 5,000 hertz. If you take the average at 5K, the Y value that we care about is just going to give us the sensitivity there. I don't want to use just the default name, so I'll disable that and give it a name that's a little bit more helpful. So I want in my memory list a value called sense at 5K. And I don't care about the X or the Z data really. I know this is going to be at 5K. So with this value that's outputting, what I want to know is what the Y value is. And here it gives a value. Again, if we run this subsequence, this data is going to be basically meaningless. There's no fundamental curve. Taking the average of an empty curve is going to give us NaN, which is not a number. This specific subsequence requires the previous subsequence to run. That's not always the case. They could be completely standalone subsequences. But when I'm developing this test, I know that I can't just open this up and run it and get meaningful data. It has to be used in conjunction with another subsequence. Now I'll create my limit step. I'll expand limits and drop in the template average sensitivity. I want to take the limit off of sensitivity at 5 kilohertz, and I'll be fairly arbitrary with these numbers. It doesn't really matter, but we'll make them pretty wide. And say if this sensitivity value is between 80 and 110, then it's going to pass. Then I save my sequence. The next thing we're going to do is create the master sequence that will hold both of these subsequences. So we'll go to File, New, and again, right away, I'm just going to save this in the same directory, and I'll call it master sequence 1. It's in the same folder. So down here in the step template library under sequence, when I expand this, it's showing you the sequences that I have in this same folder. So I want to run fundamental first, then I want to run 5 kilohertz limit. I'll drop in fundamental, I'll drop in 5 kilohertz limit. Then I'll add in a display step in this sequence. I'll take display default. We'll edit this. And let's say I want to view if this passed or failed. And I want to view fundamental and THD. Sure. I'll put those over here. And when I run my sequence now, you can see it opens up these subsequences when it runs, and it will execute them all independently. So at first, it ran my fundamental sequence, added all of this data to the memory list. Then we opened up the 5 kilohertz limit subsequence. This was referencing the fundamental curve, which was empty. But since in my original fundamental sequence, I actually created some data, when this ran, it was able to process it. So now, my result, it fails because my sensitivity is 145, which is outside that limit. But this does what I expect it to do. It takes my fundamental curve. If we look at 1K, that's too high. It's going to give me a failure. So how could this be useful to us? What other ways could we approach writing these types of subsequences? So this master sequence is saved. What if I wanted to create a limit at a different frequency and add that in? I could take this subsequence, call it 1 kilohertz limit. Then all we would need to do is change this single point from 5K to 1K. Save it. And let's create a new master sequence that references this one. So I already wrote my fundamental, so I just drop that in, drop in my 1 kilohertz limit, run the sequence again. The only thing I'll need to do is add in the display for this specific master sequence. And now pretty quickly, without needing to create a bunch of different sequences, without needing to create another stimulus acquisition analysis, I have a template that was pretty close. I just opened it up, saved it as a new sequence, then I could drop it in. And that saved a lot of time when all I was doing was adding together 3 steps plus 2 steps. The real power of this comes when you're writing sequences that do a lot more control, and it will make life a lot easier to just be able to drop in what you care about and very quickly get it. The other thing that's really helpful here is I now have 2 master sequences. Both of them are using the fundamental subsequence, but then they're using a different limit step. Again, let's say I had 100 sequences that were all using the same fundamental. And then I get word down from my boss and he says, oh, well, you know what? Instead of sweeping from 100 to 10K, let's do 20 to 20K. Instead of having to go to my 100 different sequences and make a change, I would just need to go to the sequence that has the stimulus step in it, quickly edit this, and now both sequence, the master 1 and 2, that were referencing this, are going to be updated. So instead of having to go into these two master sequences and change any settings around, I can just change that one subsequence. And now if we look at my master sequence, it's inheriting the new stimulus that I have selected. And same thing with master sequence 2. Again, if I had a lot of sequences that I was trying to update on the fly, this makes it a lot easier, and it makes it so that I know they're uniform. One isn't at a different ISO frequency. I'm not doing R40 and R10. I don't have different cycles and step sizes in between them. The stimulus that I'm testing is the same throughout, and the same with any other step type that could be put inside of a subsequence. And just the last thing I want to quickly look at here is how to drag in the steps from the sequences. So instead of using these sequences that, again, if I double click here, nothing opens up, I can't edit anything. If I wanted to just quickly write the sequence, all I would need to do is shift click there, drop them in, and then I could run those. The next thing we're going to look at is steps and sequence configuration. This will tie in a lot back to what we were doing before with the subsequences. Some of the step parameters, those come from sequence configuration. But this will contain a lot of different things we can do. There's different settings in here. And when we change the configuration of the steps and we change the configuration of the overall sequence, it's going to be able to open up some different avenues for making loops and how the sequence itself runs, that if we ignored them or some of these are pretty hidden, we might not notice them. So step configuration we can get to by right-clicking on a step and selecting configure. In this example, I right-clicked on my limit signal to noise ratio step, select configure step, and on the right, these are all of the settings that I could apply. There's a couple of different sections. We're going to break this down into kind of 3 different ideas. The first is the step logic, what the step itself does as we run it, the loop index, and if we change between overwrite data and keep repeated data. So, step configuration is the section at the top. The step logic is the information near the top of the step configuration. If we enable wait for confirmation, this is going to stop the step and make us press enter to continue. This is often enabled by default on an operator message, where it shows the operator a message, something like set device to X, Y, and Z, verify the unit is on, then press enter to continue. You often will see this too on display steps. If you have a display, maybe you want to show that for a while, you can get as much information, then when you're ready, you click enter, and it will continue running. But every step inside SoundCheck can be enabled to wait for confirmation. If you wanted somebody to wait on a post-processing step, you could enable that. You probably don't, but you could. Display step when run will show the step when it's run for n seconds. When we enable the step, that 0.0 seconds will be definable, and we can put whatever time we want in there. Again, this is most common with a display or a message step, but you could turn off displaying different types of steps. You could not display a display. You could not display a message step. On the other hand, something like a limit or an analysis step, you could enable display the step when run. Usually, this will become an issue if somebody disables this for something like a display step. If you're running your sequence and not seeing a display, make sure this is enabled. What can be a little bit more interesting for troubleshooting is the display step on fail for X seconds. This will just run the sequence as normal, but if the step fails, it will show you something. Maybe a display would be useful for this, maybe even just a limit step to tell the user right away that there's an issue, whereas if it passed the limit, you'd want to just keep running. We can also halt on pass or fail. What this will do is if the step passes or fails, depending on what you have selected, we'll just completely abort the sequence and stop running. This is the same as just hitting escape. It's just going to stop whatever was previously running. If there's a large limit that's required to pass before running the sequence, then this could be something that halting on pass or fail would be very helpful for. One example is if you were allowing the user to enter in a test level and you wanted them to enter in 100 millivolts or 200 millivolts, something like that, and they forgot to write the M, and they typed in 100 volts. You could have a just quick limit sanity check on this step and say, if you ever write above 500 millivolts, just stop the sequence. We don't want to keep running. It's just a very quick failsafe. You run the test, someone puts in 500 volts to run it, the sequence fails and stops. You could then pop up a warning, display the step when failed, and say, hey, is this what you wanted to type? Rerun the sequence. Instead of just stopping the test, though, we could jump on pass or fail. You see these two steps enabled here. And when we enable them, this drop down to the right where it says internal noise or SNR failed, these are any other step that's available in the sequence. In the last example, if that limit step failed, instead of just halting on fail, we could jump to a message step that tells the operator, the level was out of range, please enter a range between X and Y, try again. Then instead of halting the sequence, having the operator need to understand what failed, you could jump up, have them enter the number again, rerun that part of the sequence. You can also use this to loop and take multiple tests of a sequence on purpose without having a pass or fail. So I could set both my pass or fail to the same thing, maybe because I wanted to run a test 10 times. I could always set the jump on pass or jump on fail to go back to the beginning of the test. When I run it, it will just keep staying in that loop. This is what we would call branching. We can jump to any step based on the pass-fail verdict of the step, and the steps that we have in loops are indented. It's a little bit harder to see in this picture just because they're expanded. But if we look at step 7 through 14, those are indented to the right because there is a loop. We can look at the step configuration as well by clicking the plus sign and expanding the step. This is a quicker way to see what's happening in the sequence without right-clicking and configuring on all of the steps in the sequence. If you're trying to figure out the logic of a sequence you didn't write, this is a very quick way just to open it up and see what it does. So in this sequence, we can see step number 6 is a message step, continue or end loop. This is actually just going to ask the user, do you want to run the sequence or do you want to end it? We could click yes or no. And if we jumped on pass, it's going to jump to step number 7 and go into this loop. If the step failed because we said no, it's going to jump to step number 15, which just says test complete. So if we say yes, it's going to run the test. If we say no, it's going to say step complete. One other thing to note here is that we've configured this to jump on pass to number 7, but we actually don't need to. So this message step, we had a condition to jump somewhere on fail. This will go to step number 15. If we don't specify a jump on pass or vice versa, we only specify one and the other occurs, all that's going to happen is it's going to move on to the next step in the sequence, just like you had no logic whatsoever. So if this step said jump on pass to number 15, but didn't define what the jump on fail was, if the step failed, it would just move on to the next step. The loop ends at step number 14 because we can see it again has jump on pass or jump on fail options. This will jump on pass to number 7, which will rerun the test. It'll give us another acquisition, keep running whatever we're doing in the looping part of our test. And if it fails, we're going to jump to number 15, which is the message step that says test complete. Notice something else at the bottom here. We can also specify after n repetitions to leave the loop. We'll talk about this when we look at the loop index a little bit more in depth, but if this person clicked yes 101 times, on step 14, it would say, all right, that's enough data, even though they said yes, keep running. There was 100 repetitions of this step, so it's automatically going to jump out of the loop. We can use this for automation where I wanted to always test 18 times and I didn't need operator interaction. I could just have this and have the loop set, or it could just be a fail-safe where something gets stuck in an infinite loop just to get out of the loop and continue the sequence. We've talked about the pass-fail verdicts of steps. So do something if it's passes or fails, jump, halt, whatever it is. But what does pass or fail mean in a step itself? There are different step types that will have different options in pass and fail criteria. A limit step is very straightforward. You set a limit on a curve, value, or waveform. If the limit step passes, it passes. If it doesn't pass the limit step, the limit fails, and the step is going to fail. As you're running sequences, you'll get visual feedback of this in the step editor as well. If the step is highlighted in green, it passes. If it's highlighted in red, it means it fails. Message steps will ask the user a yes or no question. If you say yes, it passes. If you say no, it fails. A lot of our example sequences, you'll see this type of logic in that will say, do you want to recall example data or do you want to run your own? If you say yes, it will pass, jump based on that. If you say no, it will fail, jump based off of that. One other very common use case for message steps is digital I/O message steps. You could set a read DIO message step, and if it matches whatever you specified in there, it's going to pass. If not, it's going to fail. So I could create a loop that's waiting for a DIO to be in a specific spot. When I go flick a switch on my DIO, it goes into the configuration expected in SoundCheck, and it runs my sequence. Custom steps, these are steps that are created in LabVIEW and added to your sequence as well. We're not going to go over these too in depth, but basically in LabVIEW, you can wire a pass or fail to the output, and that pass or fail is going to be the pass or fail of the step. You could have it be logic-based, you could have it always pass, always fail, but that's up to however you design your own step. One interesting use case of these is display steps. So displays can act as an overall pass or fail logic step for multiple results. How does this work? If I display 10 different results on a single display step, what that means is if they all pass, my display step will pass. But if a single one of them fails, my display step will fail. So it is basically if anything fails on a display step that you display a result on, the display step will fail. This is a really convenient way to just say, did everything I care about pass? Then I can put logic based on my display step. Instead of having logic based on 10 different limits, if I display those 10 results on one display, I can very quickly see, did everything I care about pass or did something fail? We can jump based off of that. One thing that's really common would be to run a test once and then at the overall display, if something failed, maybe just run the test again to verify there wasn't an issue with wiring, something like that. Then if the step passes, great, you move on. If it fails again, you could branch based off of that. If the display step isn't defined here, then it's going to pass. If I added in a post-processing step and said jump on fail to this step, that step is never going to jump on fail because 100% of the time when it executes, it's going to pass. So remember, if you're using logic that you want to actually have differences on pass or fail, use these types of steps. But it might be perfectly valid to always want to jump. So you would just say jump on pass. That step's always going to pass. It's always going to jump. The loop index is the section at the bottom of step configuration. This is where we would define after n repetitions, jump somewhere else. The thing that's really helpful about this is that it creates a memoryless value that increments according to how you defined it. So by default, it will create a value called loop index that starts at 1 and increments by 1 every time. So the first time you run a loop, it'll be 0. Then the first time you loop, it'll jump and say loop index 1. But what we could do is make this a lot more specific to what our use case is. Let's say we were going to jump around and do a turntable test. I wanted to test my turntable at 10-degree increments for 180 degrees. I could say after 18 repetitions, jump out of the loop, and then in the name of my loop index, instead of calling it just loop index, I could call it angle. I'll start at 0 and increment by 10. I can change the unit between log or linear, and this only is the y value. This is really only one single value. We can't have an x or z attached to it. But what this will actually do is it's going to be available for us to view on displays to quickly see which angle we're on. It's going to be available for us to use in the memory list if we wanted to, say, add together a stimulus level. And it's going to change the names of our data as well. So if I looped and I wanted to have 18 different curves that were all based on my degrees, I'll need to set my analysis step to keep repeated data, which we're going to look at in a second. But that repeated data, instead of just being fundamental 1, fundamental 2, fundamental 3, anything like that, it's actually going to be prepended by the loop index of the loop that created it. So instead of 1, 2, or 3, it would show me 0 degrees fundamental, 10 degrees fundamental, 20 degrees, etc. So having a loop index that's actually related to what you're trying to test is very helpful. It could just be you want to start at 0 and increment by 1 and just have curves named 1 through 5. That's a totally valid use case. But if you're going to be doing something with the value, you could set that in here. So now let's talk about overwrite versus keep repeated data. What overwrite means is anytime it sees a curve with the exact same name, it's just going to overwrite it. Let's say I had a loop and I loop up to an acquisition step that creates recorded time waveform. If I have that set to keep repeated data, it's always going to overwrite my recorded time waveform. Sorry, if I have that set to overwrite data, it's going to overwrite that waveform. If I have it set to keep repeated data, it's going to create multiple items in the memory list and save them all. So the question becomes, which one do we want to use? Do we want to keep repeated data? Do we want to overwrite data? What's the goal here? So let's actually look at a sequence that we've kind of been talking about. I'm looping an acquisition and analysis step to get fundamentals of different angles. I want to get 0 degrees, 30 degrees, 60, 90, etc., up to 180. It's just a very simple sequence. I define a stimulus. I have an acquisition and analysis, steps 3 and 4, and I want to loop steps 3 and 4 a set number of times to try and get my data out. And remember, we can change these on a step-by-step basis. If we look at this first example, my acquisition step, number 3, is set to keep repeated data. One thing to keep in mind is that if it's set to keep repeated data, there will just be no specification. If it's set to overwrite curves, like it is in my analysis fundamental, it will tell you overwrite curves. So when I expand my data out and my step configuration, if it doesn't say overwrite curves, it's keep repeated data. If I right-clicked and selected configure step, it's just going to show me which box was selected. But in this case, I have an acquisition step that's creating a bunch of different curves. But that becomes a bit of a problem for me, because if you think of my analysis step, step number 4, I want each time it runs, I want a new waveform, the most recent waveform, to be fed into my analysis step. But I can't do that because I'm keeping repeated data, and my fundamental of analysis is only pointing to the 0 degrees of recorded time waveform. So if I ran this step in a loop, I'm going to get a bunch of different waveforms, but I'm only getting one fundamental. So what's another way to approach it? I could instead have 8 different analysis steps that are pointing to different waveforms, but then every time I run it, it's going to give me a new analysis step. Those analysis steps are going to keep repeating themselves. Most of the time, they're going to be blank curves, so it's going to be a lot of unnecessary data calculation. So what I could do is configure my acquisition step to overwrite. Now, this is still looping the same amount of times, but every time I'm outputting one waveform called recorded time waveform. If you look in my analysis step, step number 4, it's always inputting recorded time waveform. Great. Every time I run, it's giving me the most recent fundamental. The problem here is when I finish my sequence, all it's really going to show me is one curve named fundamental, and that will be my 180-degree curve. I won't have all those other curves I ran because my analysis step is set to overwrite. So when I overwrite it, it overwrites it. Instead, if we set the acquisition to overwrite and the analysis to keep repeated data, every time we run, it's going to update the recorded time waveform, feed that recorded time waveform into our analysis step, and that analysis step is going to keep the fundamental for each of the degrees. So we get 8 different curves at the end, but we're overwriting the waveform. So in a quick example like this, where I wanted to get just the curves at the end of the day, I'd want to have a mix of overwrite and keep repeated data. But that brings up another issue where what if I wanted to save the recorded time waveform? And I don't want to write 8 different things. So to kind of work around that, we could put an autosave step inside of the loop. What it's going to do is every time it loops, it's going to save the most recent curve to disk. Since we're overwriting it in memory, we could change the autosave step to append. The analysis step or the acquisition step and recorded time waveform, they're always sending out the same name, the same curve, the same waveform. Then we could just take those and save them all to disk, maybe append them to the same file. So our autosave step could be append the name of this sequence run with this serial number. When I run my loop, it puts all of the fundamentals from that serial number into the same file. I could open them later and investigate it, but it's not cluttering my memory list, and it's all saved to disk and available for me to use. So there's some different ways you can approach this when you're changing between overwrite or keep repeated data. So keep in mind what you're trying to do, what you need saved to disk, what you need saved to memory, if anything needs to be calculated later in SoundCheck, and make sure those configurations are set correctly. And then if you need them to be saved within the loop, I'd recommend auto-saving with overwrite data. If you're using keep repeated data, I would recommend the autosave to be outside of the loop. So if we went back to our previous example over here, if I wanted to then save all of these curves, 0 degrees through 180, I would take an autosave step outside of the loop and point to those 8 discrete curves. So I run the loop, then to the end of the loop I save them. where in this case, it's saving within the loop. There's going to be some time changes depending on that. The sequence will run faster in certain ways. If there's less saving, it's going to be a little bit quicker. There's going to be some other trade-offs there, and it really just depends on your use case. Instead of just configuring a single step, we can configure the sequence. Every sequence we create, at the very top, there's going to be a step that looks like a step that's called overall sequence. And to configure the step, we just double-click on overall sequence. We can change what happens when the sequence opens, starts, and runs. Some things that are really helpful would be if the sequence opens, you could preload the stimulus. What this means is if the stimulus step is always the same, when it first opens, it will just calculate it and put it into memory. Now when my sequence runs, I'm not spending processing time calculating a stimulus. Where this will hurt us is if we're actually changing the stimulus on the fly by using a memory list item. So if I'm changing my stimulus around, then that means that value could change as the sequence runs, so I can't preload the stimulus. I need to disable this. If you ever get a warning that preload stimulus is on when you're using memory list items, go into the sequence configuration, disable preload stimulus. We can also have sequence documentation. On the bottom left, we could enable open instructions file. If you've ever opened one of our default sequences that ship with SoundCheck, you'll notice that a PDF opens alongside it. What this will do is just open up whatever file that we browse to if open instructions file is enabled. If you wanted to open up the instructions on how to run a sequence, you could enable this, point to a PDF yourself. When the sequence opens, it'll open that file. Also important to note here, if this isn't working the way you expect, there is an overall SoundCheck setting for this. If you go to Edit Preferences, you can enable or disable opening an instructions file globally, and that will overwrite the local sequence setting. The right side, when sequence runs, update data and displays is useful, but all the other ones, the display all steps, displayed fail steps, wait for confirmation, etc., those are a lot more helpful when you're trying to troubleshoot or debug a sequence. You could put those on to display all the steps, make sure everything's working. But if you're actually going to run a test, these will take a lot of time. I'd recommend disabling them. Sequence parameters is where we can add in blank curves, values, or waveforms. We saw an example of this when we ran our subsequence test, and we'll take a look at it later when we set some values using TCPIP. It's a way to get a placeholder curve into the memory list so you can actually reference that as you're writing the rest of your sequence. But the two most common use cases for it are external control, when you're going to be setting these externally, or something like a subsequence, where you know you're creating a curve or value and you need to reference it, but it doesn't exist yet. All right, so now let's look at a hands-on for step logic. In this example, I want to take an RTA spectrum of pink noise that's output from my device under test. And what I really care about is how it behaves with different levels. I want to test it at all of these voltage levels listed here. I could create 5 different stimulus steps with different levels and then point them to different acquisition steps and analyze them all. That's completely valid, but it's not as quick and it's not as flexible. So instead, we can create a loop, use the loop index value to make our settings and create our stimulus level and automatically change the level on the fly. So I'm going to, again, open up SoundCheck. We sent a hands-on for this as well. Definitely recommend you try this on your own, but I will give a warning here. In this sequence, we're iterating over levels and increasing voltage. If you set this incorrectly, you could have an infinite loop and output infinite voltage. You could have the wrong value set somewhere and start adding in dB not the way you're expecting and start outputting 20 volts instead of 100 millivolts. My biggest recommendation for this would be to write the sequence, don't connect your speaker, run it a couple times, make sure that the levels are what you expect when you look at them, make sure the stimulus and waveforms are updating the way you expect, then connect your device and run it. So, to get started now, I'll open up a new sequence. I'll move it somewhere else, just put it in SoundCheck and call it loops. Doesn't really matter where this one is, so we can save it wherever we want. I'm going to add in a message step template called enter test level. And then I'm going to rename this to starting test level. With these types of message steps, whatever the names are what the values in the memory list are created as. So I would highly recommend setting the name first before you start writing your sequence, because if you later change the name, it's going to change the value. I don't really care about a message. I'm actually not going to display this. All I want to do is add a value to the memory list to get started with. And I want to work in log scale. So I'm going to change this from linear to log, set the default value to -40. And we talked about this step configuration before, but I'm going to right-click, configure step, and disable display step when run. So now when I run my sequence, absolutely nothing shows up, nothing really happens, except I now have a -40 dBV value in my memory list ready for me to use. So if you ever need to just create a value in SoundCheck, you could use a message step, disable display, and it's just going to put whatever the default value is into memory. The next thing I'm going to do is just add a step that we're going to be using later, curve plus constant. I'm not going to do anything to it now. I'm just going to change the name of it. But this matters a little bit just because I need to put it somewhere to be able to create my loop. So I need a step placeholder to be able to loop to. That's why I'm putting it in here. Now I'll quickly write a sequence. So I want pink noise out of my amplifier. I want play and record out of my amplifier into my reference mic. I want an RTA spectrum, and then I want to look at it. So here's my test sequence. If I run it right now, it's going to give me an RTA spectrum, basically completely independent of a loop. It's just giving me spectrum at one level. Now let's create our loop to increase the levels. What I want is this analysis step to jump to this post-processing step, and every time it runs, add in 5 dB. So to get started here, I'll configure this step to jump on pass to stim level calculation. Remember, this is an analysis step. 100% of the time, it's going to pass. After 4 repetitions, I want to jump to my XY graph. So it's going to jump up to stim level calculation. After 4 repetitions, show me my display. I'm going to start at 0 and increment by 5. I'll call this voltage loop and set this to be dB. So it's just going to be 5 dB. I'm going to take this value, and then eventually what I'm going to do is add it to my starting level. So as we increase, it'll start at 0. Minus 40 plus 0 will play out minus 40. The second run, minus 40 plus 5, play minus 35, etc. Then what I want to do is enable keep repeated data. If I don't do this, it's going to overwrite my curve and only show me the most recent one. I want to show me every curve that's calculated from this step within the loop. Now I can actually go back and edit this. I'll take my post-processing step, take the starting test level, and add to it the voltage loop. This part's very important. Make sure we're set to addition, work in dB. If we don't have this set correctly, our math isn't going to do what you expect, and we could send out way too high of signals. Again, highly recommend just running this, looking at the values before we actually put it through any hardware. I'll call this stimulus level. I don't need the X or the Z data. All I want is the Y output. There we go. In my value, I have something called stimulus level. How do we actually apply this? Go to our stimulus. Right-click on the current level and change this to memoryless selection. I'm going to use stimulus level and the Y value. I don't want to be using the X or the Z. Those don't exist. I want to be using the Y value. When I close this, I get a warning. What does this mean? Memoryless value is being used, but preload sequence is on. Turn off preload stimulus. We talked about this a little bit before. Since I'm calculating the stimulus on the fly, I can't preload it. I need to open up overall sequence, and in the top left, disable preload stimulus. There's also a couple of things I want to do here. I also want to open the first display step when the sequence opens, and to update the data in the displays. Why is this helpful? If you look at my loop, I actually don't display anything until the sequence ends, but if I update the data in my displays, as the sequence occurs in the loop, it's going to show me the new curves come onto the graph, which is what I want. So that's personal preference. We could set that however we want. But what I want to do is run my sequence and see all of those curves. So now I want to display all of these responses on the graph. I'll put them on here. I want to be able to see which curve is which, so I'll enable auto size legend. Here's my graph. I'll save my sequence and run it. And this is basically what I'm expecting. The blue curve, the first one, I was talking over it, so it looks a little funny. And below about 200 hertz, my speaker's not really outputting any data, so that's all noise. But within the passband of the device, I'm now seeing an RTA spectrum at the different levels, increasing by about 5 dB stimulus level on each. And with this, I could change this as much as I wanted. Right now, if I look at my stimulus level, I could see it ends at -20. My starting test level is -40. If I wanted to change my starting test level, all I would have to do is go in here, change the initial start. Or if you go back to this analysis with configure step, I could change how many times it repeats. I could change the increment if I wanted 3 dB level, if I wanted 20 dB. I could set those all within here. So again, highly recommend setting this up yourself, trying to run it. There's a couple of bonus questions that will help work through changing names and different ways to approach this. We don't actually even need the starting test level. We could just feed in the loop index right from the beginning. There's a couple things you could do here, and it's really just dependent on what you're trying to do in your test, how you're trying to increment it. All right. So the last section we're going to talk about is TCP/IP control and using it to talk with SoundCheck. These commands can be sent or received through any programming language, any operating system. You could send it to your local computer. You could send it over a network. It doesn't matter. It matters what is running SoundCheck, what operating system is on that, but where the command's from, SoundCheck doesn't care. It's completely agnostic. It doesn't matter that we gave you an example sequence written in Python. It doesn't matter that it's in LabVIEW. As long as you can send these TCP/IP controls and commands, you can talk with SoundCheck. You can even write your own language if you wanted to, which I wouldn't recommend, but you could. The test data and results are returned. So when you send commands, you can get data back. They're in a JSON data format. We'll look at that a little bit more specifically, both in specific use cases and just in general, how they're formatted when they come back. TCP/IP must be enabled in SoundCheck Preferences menu with the specified port, and it has to be allowed through your firewall. If you don't allow traffic to come through TCP ports to that machine, SoundCheck is not going to receive the commands. It's not going to do anything. So I will quickly just jump over there right now, and we'll close this sequence. So up in Edit Preferences, on the Advanced tab, this checkbox at the bottom to enable the TCP/IP server must be on. And when you first turn it on your machine, you're most likely going to get a warning through your operating system that asks you if you want to allow the traffic through the firewall. Say yes. By default, we use port 4444. It's very arbitrary. You can change that to whatever you want. But all of our example external control sequences will use that port. So feel free to change it if you need to. Just keep in mind when you go use any of our example sequences and example external control programs, you would need to change the port that those are accessing. Another very helpful setting in preferences is the suppress dialogues option. If you go back to the same spot we were just in, Edit Preferences, under Advanced, we can enable suppress dialogues. What this will do is just prevent SoundCheck from generating any dialogues that might halt or pause the sequence. Maybe if you've ever changed sequences in SoundCheck, you've noticed a pop-up that says, do you want to save your curves? And you have to save them or discard them, and you could set a default setting to it. Or maybe you've changed sequences and seen some notifications about something changed and something's running, and you just have to click OK. Maybe there's a login. If you are not physically sitting in front of the machine and trying to just tell SoundCheck to run, and a dialogue like that pops up, it's just going to sit there waiting for SoundCheck to respond, but SoundCheck is waiting for somebody to tell it what to do. You could disable or enable suppress dialogues, and it will just squash all of those messages. This is really only recommended when you're using external control for unattended access of SoundCheck machines. If you enable suppress dialogues and you're trying to edit your sequences, there's a lot of dialogues that you want to show up and tell you hey, this is setting correctly, this isn't going to work, etc. And some critical errors that are going to stop the sequence from ever running will be hidden as well. So it's a very broad stroke, just I don't want any messages option. So if you are using external control, you don't want any messages whatsoever, you're done with developing the sequence, you've handed it off to someone else and you just want to run it, this is very useful. But if you ever turn it on and you're running into some issues, this might be something to take a look at. You can actually enable this option through external control as well. So maybe you ran an external Python script that disabled all dialogue so you would just be able to run your sequences. Then when you go back and start editing, you're missing a bunch of pop-ups for information. Go back, double check what this dialogue is set to. So there's some common TCPIP commands just to kind of give you an idea of what could be done. You could open, run, and save sequences. You could set or get the login level. You could get or set the serial number. You could retrieve the name of the sequence, a list of all the steps in the sequence, all of the names in the memory list, and then data from the memory list. So a really common thing to do would be get all of the names that are available in the memory list, and then for all of those names, iterate through and get all the data for those names. Or if it's a sequence that you've already written and you know all I care about is the fundamental, you could just say get data from the curve named fundamental in the memory list. It'll pull it back into whatever operating system you're using as a JSON. So if you wanted to actually use one of those commands, this is where, again, the SoundCheck manual is a really great resource. This is something that the characters, the case, the exact formatting is very, very specific. So I always have this open as I'm trying to write my external commands, anything I want to do, just to make sure the format that I'm writing in or trying to get back is what I expect. It's also pertinent because we've added new commands. This has been available in SoundCheck for, I believe, 4 versions or so. And in each version, we've added new things. Example is in SoundCheck 18, we allowed the option to set memory list. If you tried to open up a SoundCheck 14 sequence in SoundCheck 14 version of SoundCheck and tried to set a memory list value, it's not going to work because it doesn't know those commands. So using your SoundCheck manual, whatever you're trying to do, that's going to be in there. It's going to tell you exactly how you can do it. It also gives some instructions on how to run the example apps. We include some example applications that will give you external control command. We'll take a look at some of them today, but not all of them. And it will go over how they're used, what they're doing, and just basically how you should run them. And again, the command set definition for rules and how to format the communication and the full list of commands is available in here. So I'm going to pull that up on my end real quick. Okay. So in the TCPIP chapter, it's going to give us what the command set definition is and tell us how it conforms to these rules. So if you're reading through this, it's telling you we need to have period separated command segments, what the different parameters are, how to use the quotation marks, the fact that they are case sensitive. That's a very important one. If you are trying to write these and do not have the correct case on them, you're not going to get anything back. It will then also show down here the command list and the return format. So if we look over here, the command and the parameter, it'll show you what the command is, what the parameter is down here, then what that means. It'll also give you a little bit of a description and what the return data will be. The data type, we have a chart up here, how you can interpret some of these numbers if you want it to be, or if you're expecting a Boolean, if you're expecting a string to be sent or returned, that's going to mention it up here. But in this case, for example, the first one, to set a login level of a technician, we would use SoundCheck.setLoginLevel, parentheses 1. Will we execute that? It's not going to have any return data. That's void. And it's going to set our login as a technician. So all of these commands are over here. When we start seeing some of the data that will return something, if you look the other way, at the get login level, this is going to return a value as either 0, 1, or 2, if we're an engineer, technician, or operator. So when I send that command, what it's going to return is value with whatever it actually is from this list. So look through these commands. There's a lot of different options in here. There's a lot of things you can do. And again, it's very specific for how it's configured. We'll look at a couple of common ones, a couple of use cases for them, but we're not going to go over every single one. There might be something in there that's perfect for your use case that we're not going to talk about right now. So go ahead and read it if you're interested in adding these. Every command you sent will return a JSON formatted text string with this information. Command completed will return true or false. It'll return true if the command was recognized and executed. The one thing to keep in mind here is that this is really just in SoundCheck's point of view. If I tried to run soundcheck.save to save my file, but I didn't have write permissions on my operating system, I would still get a true here because SoundCheck is looking at my command, says, oh, okay, I know what soundcheck.save means. I told it to save. We're good. That's true. So if you're getting blocked by your operating system, then that's going to still come back as true. But if this comes back as fail, then you might have a typo. You might not have the communication with the other device you're trying to talk to it with. So very good for troubleshooting. Return data is dependent on the command set. This is what we were just looking at when we were in the manual. This return data over here, whatever the command we send is, if it has any return data, will get filled in to the return data. Same thing with return type. If there's a type that's getting returned, it's going to tell you that. Error type and error description are going to be for troubleshooting. If anything kicks back with an error, you could get some information from here. And original command and resolve command, these should be the same. If you send a command, the resolve command should be the exact same as the original command. This is really something for troubleshooting. If the original and resolved don't match, you're going to need to figure out why. Again, is there communication? Are you getting some sort of error? Is something lost? But what we really are using, if there's any return data coming back from SoundCheck, it's going to be coming back in the return data field. So let's look at an example when we're trying to send a command of the same type. If we're trying to run SoundCheck set serial number and SoundCheck.get serial number. So if we look in the manual over here, we could run through this, try and find out where the serial number option is, and it's going to tell us what we're output data we're expected to get back, and etc. So I just copied it out. Oops. Into the slide here. And this is what we're going to expect with these two different commands. So they're both involving the serial number, but one is set and one is get. So if I'm trying to run soundcheck.setSerialNumberSpam, it's going to tell me my command completed was true. The return type is void, so the return data should be blank, which it is. There's no error, so both error type and description are blank. Then my original command should meet exactly with what my resolve command is. It does. I'm happy. I just set the serial number as something. I now want to get it. In this case, everything else is true. Everything else, the original matches the resolved, so I'm happy there. But the return type is now a string. And the return data is the value, and then my actual serial number, so it's spam. So this is the JSON that I get when I send both of these commands. So even if we're setting something, we're going to get data back, and then if we're trying to get the data back, that's going to come back and return data. So one thing that's also very helpful for this is to look at one of the examples, which we'll do, and we can kind of see what's happening there. But the other type I want to look at first before we open up and start going through this is the memory list.set option. So memory list.set will give us control through TCPIP to set curves, values, results, or waveforms. And remember, it doesn't create anything new in the memory list. There already must be a placeholder that exists, usually used in conjunction with sequence parameters set in overall sequence. When we're configuring the overall sequence, another thing to keep in mind is that clear measured data must be disabled when the sequence runs. If not, we're setting these values externally, running the sequence runs, it clears all our memory list data, we get blank values. So in configure sequence, make sure we disable clear measured data. Why is this helpful? So instead of creating a bunch of tests, I could use a single sequence and then externally set everything. We just looked at two examples, both with subsequences and with sequence logic, that could also have just been accomplished with external control. This is especially helpful if you already have a full system and SoundCheck is just one part of the test suite. So I wanted to run my one test set in different levels. I could run the same sequence, but have memory list.set stimulus level with the level I want, run the same sequence, change it in my external control. There we go. It's everything that I was trying to do. Can just be done by setting these values. The setup is a little bit more specific as well for the memory list.set. Again, I highly recommend just looking at the manual. But if we look at how we would send a command to set a curve, I would need to define a lot of things about it. I would need to give the curve name, so whatever it is I'm trying to write in the memory list. Maybe it's something called fundamental, maybe it's a limit curve. Then I would specify, excuse me. Then I would specify all of this data here. You need to copy this exactly. It has to be everything filled out. And you would just give it X, Y, and Z data, give what units are used on each of the axes, what scale, what the dB reference is, what the axis scale are, if it's protected data. All of this stuff can be set externally. We include a lot of examples in different languages in the SoundCheck folder under external control examples. A lot of these are useful out of the box. You can just take them, kind of see what's happening. But they all also include the source code. So if you want to take them, tear them apart, see how they were written, how they're communicating for these different languages, take them, make copies of them, start looking into them, see what they're doing, how they're communicating, and then write your own. So now I want to look at a couple of those applications that we have and just kind of see what they're doing and how we can get some ideas from them. So the first one I'm going to open is LabVIEW. So under my SoundCheck 18 folder in external control examples, we have these other 5 folders with a bunch of different examples in them. So the LabVIEW one, and again, we have the source, so how it was actually created, and then the application. So if you want to use these as starting points, we highly recommend that. This application is very helpful for just kind of looking and seeing the commands as well as the responses. So if I wanted to run soundcheck.getStatus, I can just highlight it down here. It's confirmed I'm connected. I click execute, and it returns the status. It might be a little bit hard to read, but down here in the bottom is the response JSON I got. So what I really care about is this return data. The busy is false. So the status of SoundCheck is that it's not busy. We could also set serial numbers, and it gives us an option right down here and separates what the string parameter that we want to set versus what the actual full command is. So if I wanted to write 1234 to my memory list, then the full command is soundcheck.setSerialNumber, parentheses, 1'1234. I click execute, and if you look back in SoundCheck, you can see my serial number is now 1234. If I change this to something else, hop back to over here, I could instead try and get the serial number, and it returns the value, 5678. So I think this is really a good intro to one because you can see the exact commands, see how they're returned, then hop over, open it up as the source code, and see how we wrote these. The other option that we have a lot of data included with is Python. Most of the questions we get, most of the people that are trying to use integration with TCPIP and SoundCheck have requested Python. So as a result, it's just a little bit more fleshed out. If this isn't what you're interested in, you're more than welcome to use any other programming language. Again, anything that can communicate will work fine. But the good thing about Python is we do support it with a lot more built up than some of the other languages. So if you're looking for a place to start, I would recommend Python. We include a Python library. And in addition to some of the other commands in here, we have some options in classes right out of the box for you. You can install and start running instead of having to write all these commands yourself. You can just use all of these methods, all of these classes that we have. We have options to set an ini file, for example, to suppress all dialogues. You could do that directly from this Python script. So recommend reading through this if you have any interest, as well as the README here, which will tell us how to run some different external control examples that come with SoundCheck. So first, it has the instructions for how we would need to do it. This is how we need to configure our machine. We're not going to cover that now. I'm going to assume that Python is set up and running. and we'll take a look at some of the examples we have with SoundCheck and how they get data returned to us. So one of them, just a very straightforward example, is this simple SoundCheck example sequence. Script. If you go over to Python and script, something called simple SoundCheck example. I'm just going to hop over and I will just run this command. Basically what this will do is it's going to run through, open up SoundCheck, setting a random lot number. We just arbitrarily set 1, 2, 3, 4 as the lot number, retrieve the login level. So my login level is 0. I'm logged in as an engineer. It opens up complete test, and then it gives me my run result. Was it a success? Did it pass? What was the margin of my pass? Here are all the curves that are in your memory list name. And then it will actually get the data from my fundamental and plot it in Python. So it's taking my fundamental data, putting it into memory. Now that exists in Python. Once it's done, it actually just closes out SoundCheck. I don't even need to open it. I don't need to look at SoundCheck at all. If we open this back up, I want to look at an example that will kind of accomplish what we talked about in the sequence loops and logic. So our goal there was to try and run a sequence, loop the stimulus level, and increment it by 5 dB a number of times. To do that, we used sequences, we had loop stimulus levels, and added them together. Very similar to that setup, I could use external control to accomplish the same idea. So I have a stimulus that's looking for a level called stim level. Where does that come from? This is a value that I created under sequence parameters. Again, very important that when sequence start, cleared measured data is off. And in this case, I want to update my data in the displays. I could go over to SoundCheck, and if I ran a very simple example, what I'm doing is setting my memory list value. I'm using the SoundCheck TCPIP library, and all I have to do, the only thing that I wrote, was specify at a level, made a loop, and set a value with a value named stim level, where the Y data is my level that's increasing in the loop. Then at the end, I'll run the sequence. So as I execute this, it's going to set different levels. Then in those levels, it's going to keep increasing them. And here, very similar to what we got by using sequence loops and jumps within SoundCheck itself, I can just feed that data externally. And now here's my stim level. It went from -40 to -20 dB, the exact same way that we did in the loop. Again, there's different useful benefits and features of this versus making the loop itself. When I wrote it this way, the data is not actually saved multiple times in the memory list. I'm just displaying it together. But we are overwriting since it's the same sequence. I can't keep the repeated data. I just have to overwrite it and protect it. But if I was trying to do this and put in different levels, different ranges, it's something that you can do it in both SoundCheck with the loops, or you could do it in an external program. But maybe you're more familiar with an external program. Maybe it's already tied to your other testing, so it might be a little bit quicker. The last example I want to look at is the frequency response example that comes with SoundCheck. With this, we can change arguments within the command itself and specify if we want to launch SoundCheck, shut it down, give it a level, give it a frequency start and stop. And this is included with SoundCheck. If you want to run this, you can just open it up and find the sequence itself to run it. So if we went to SoundCheck, there's frequency response.py. And this is going to tell me how to do it. I could use this or the README. And I could say I want the level to be -20. I want f-start to be 200. I want f-stop to be 10,000. And as I run this, here's my level. I played out a test level that we set through Python. That level was set to -20 dBV. Then a start frequency and a stop frequency, 210K, that were then used in my stimulus step. So test level, start and stop frequency. If I made changes to these, you'd be able to see right inside the sequence itself what the new test frequency was, what the new test levels were. So now I'm sweeping from 20 instead of just from 200, and it's reflected here in the graph. Again, this is very powerful. We include these examples right with SoundCheck, so highly recommend. All right, thanks everybody for joining today. Hopefully it was helpful. Hopefully you learned something new. Again, what I would recommend right now is try writing sequences with this information. Try following the hands-on. Open up some of the external control examples. Run the example sequences. Look through the README. And we have a lot of resources available. You can go to our website for different resources. And if you have anything that we didn't talk about during this training, some specific use case that you want to go over, please give us an email at support@listeninc.com. Open up a support ticket, give us a call. We'd be more than happy to help. Thank you, everybody, and I appreciate your time.